All right. Okay. Well, hi, welcome. Thank you for tuning in to this. So I'm Jeffrey Bunning, and I am a PhD candidate at the Australian National University, or at the Research School of Earth Sciences at ANU. And this is part of Mount Stromlo's, which is the Research School of Astronomy and Astrophysics at ANU, part of their celebration of International Asteroid Day, which is on the 30th of June. So I'm recording this on the 29th of June. So that's tomorrow, which is very exciting. So we're going to be talking about asteroids, of course. Now, as I go through this, we're going to be asking a few questions about asteroids, like one, what are they? Where are they from? How do they get here? We have things like meteorites. They're on the ground. They end up here. How do they get here? And how do they get into near-Earth space in the first place? We've got these things whizzing past the Earth. You hear about near misses all the time. How do they get there? Where are they coming from? So we're going to be looking at those kinds of questions. Now, to start off with, what is an asteroid? Well, this is a bit more the history, actually. It started out when astronomers were looking in the space kind of between the planets, between Mars and Jupiter in the 19th century. And they were looking for a planet. They didn't find one, but they saw these very small, dim objects moving across the background of stars, and they called them asteroids, which means star-like. So they looked kind of like stars, but they're a bit smaller. And now, obviously, we know that they aren't little stars. They are little pieces of worlds, really. Fragments of broken planets or primordial building blocks of planets in some cases. So when we talk about asteroids, we're often talking about something that's mostly rocky. It doesn't have to be. It could be metallic as well, and we'll look at that later. But we're talking about anything that's bigger than a meter, but smaller than a planet. And planet has a bit of a interesting definition because you have to have cleared the orbit. So you don't want asteroids. If there's other asteroids that are in your orbit and you're sharing with them, but not because of you, then that you're not really a planet. So asteroids are anything that's smaller than that. They haven't cleared their orbits yet. And when they're this small, it often means that they're irregular shapes. They aren't nice and spherical. Like the big planets are all round. And that's another category of a planet, or another rule to be a planet is that it has to be spherical. And the asteroids are too small to do that. They haven't rounded themselves out yet. So they are often like this. So these are potato and ginger shaped in some cases. So this is Eros. This one is about 30 kilometers long. And this is Itokawa. And this is a near-Earth asteroid that was visited by a Japanese spacecraft in 2006, I think. It landed in 2011, or maybe it launched in 2006. It came back in 2010. I got those dates all mixed up. But yeah, so that one comes by the Earth all the time, and it's about 500 meters across, so it's quite large. And this one, so they can also be this kind of shape. This is a spinning top kind of shape. And these ones are kind of thought to be, and this one could be as well, rubble piles. So whereas some of them might be monoliths, single big rocks, some of them are just piles of rocks. And these kind of spinning top shapes that are common, this is Ryugu and Bennu, and they are also on the scale of, I think, Ryugu is about 1 kilometer across, Bennu, I think, as well, is about 500 meters. And they are, they don't necessarily have a single rock inside them. They're just a bunch of rocks together. As you get bigger, they often get a little bit rounder. And you have Vesta here, which is a bit more of a potato shape again. You can see Eros down there, that other one that we looked at, which is 30 kilometers across. And then we have Ceres, which is a dwarf planet, because it has a lot of the other features in terms of it's fully rounded out. In a lot of ways, it's a fully realized world. It just hasn't been able to clear its orbit of the other asteroids because it's right in the middle of the asteroid belt. So it's the biggest of the asteroids or the smallest of the planets, if you want to think of it that way. And then Ceres, again, is actually much smaller than the moon, than the Earth's moon. Now, just to give you some scale, this is Itokawa. So this is, if it was on its way to destroy Paris, it would be a lot more, gas, and it'd be glowing hot as it kind of came down. But it would look a little bit something like this compared to it, and that would be very bad for Paris. Now, we call the pieces of them that actually fall to the Earth meteorites. So meteorites and asteroids, we're talking about the same kinds of things most of the time. One problem is that we don't always actually know the connection between a meteorite type and what this rock looks like and which asteroid type that belongs to. We're not actually sure all the time, but we know that they're the same object. And the meteorites are just pieces of these asteroids that have fallen down. So the name itself, means sky rock. And when they fall to the ground, they look a lot of times something like this, a dark rock. A lot of them are found in places with light-colored backgrounds. So that can be places like the Sahara or Antarctica, because it makes them a lot easier to identify. They're very flat terrains, places where they stand out. If they fall in a dark place, or places with dark rocks and stuff, they're a bit harder to spot. And that dark is the fusion crust, and that's a layer of glass that was, so as this fragment of an asteroid entered the Earth's atmosphere, it heated up and melted in that outer layer. And made a kind of glassy layer, and that's our dark fusion crust there. So if you're ever looking for a meteorite, yeah, you're looking for something that's often a bit rounded and dark as well. Now, what are they made of? Now, as I was saying before, they are often made of rock, but that's not always the case. Asteroids aren't always made of rock. They can be metal. We have a lot of metallic iron meteorites in the Earth's impact record. There are also things that are a mixture of metal and rock. So some of these are, the fragments of cores of planets. Some of these are from where the core and the mantle of a planet meet together. And some of them are, just all rock. In some cases, that's because they're the crust of a protoplanet that was destroyed, a baby planet that was broken apart, or because they are, we'll talk about them later, but a primitive aggregate of what was floating around before the planets formed. They can also have ice as well. Ice is another component. So one group of meteorites called the Carbonaceous Chondrites, they often have a lot of water in them. So they can have up to about like 10 or 11% water bound up in their minerals, often in clays and things like that. So they're kind of so their parent asteroids would have been something like a mud bowl, especially when they were warmer and initially formed and hotter. They would have been like a mud bowl world, some of these things. And Ceres, that biggest of the asteroids and smallest of the dwarf planets, is a little bit like that itself. So it's got a rocky interior with an icy layer on the outside, potentially with water in there sometimes, especially after an impact. You might melt a layer of that, and some dust and rock on the outside of that again. So these kind of mud bowl worlds are something that happens when you start to add that rock and ice together. When you add enough ice, then you start to get a comet. And so there isn't really a sharp line between an asteroid and a comet. A comet just has more ice in it. And often what makes it a comet is that it's on a very elliptical or oval-shaped orbit. So it might be coming from out of the solar system, the outer solar system originally, falling close to the sun, heating up, evaporating lots of gas as that ice heats up. And that leaves a big tail behind it. And that's the tail of our comet. But like I was saying, there isn't a sharp distinction between asteroids and comets, because sometimes asteroids actually do this themselves. So Bennu, where there's a NASA space probe right now, OSIRIS-REx, observed this emission coming off of Bennu. And so you get this kind of jet of rock, this spray of rock coming out of it. And so it's what we call an active asteroid. And it's something that's kind of between being a comet and a regular rocky asteroid. And that might be, we're not actually entirely sure what caused it, but that might be because if there's some ice beneath it in the surface. And as it gets closer to the sun, it heats up, that ice heats up and evaporates and blasts off some of that rock. So how do they form? Where do asteroids actually originally come from? Well, like actually almost all the solid material in the solar system, well, all of it, it was originally stardust and dust in nebulae. And nebulae are these clouds that you see. If you ever go out to the country and you look up at the night sky and you see the Milky Way, and you can see this dark band through the middle of it. And that dark band is clouds of nebulae. And a lot of the actual darkness from it is the dust absorbing the light or scattering the light from stars. So this is one looking a little bit closer. This is the Orion Nebula. There's a star-forming region actually not relatively close to us in terms of the galactic scale. And so it's a huge cloud where stars and baby stars and planets are forming actually right now. And the dust from this will eventually form planets and asteroids. And so some of these asteroids that we have, we call them chondrites, are basically just, if you were to squish down the dust in this kind of thing, you were to squish that in these kind of nebulae and squish them down into a rock, you get something like a chondrite. You get this everything, like the rock and the metal are all finely mixed together. You have those ices as well that are sometimes in there. So you have all the building blocks for a planet, kind of compressed into this rock. And then if you get enough of that together, it starts to heat up inside. So you have, so say we get enough of that primitive material together, we build a world. The heat inside that world can't actually escape, and it starts to melt inside. And when you melt it, that metal, that fine-grained metal, starts to clump together and sink to the core and form the core of the planet, like on the Earth, whereas the relatively light rock floats to the outside of it. And that forms the mantle and crust of the world that we're building. And if there's any ice or volatiles on it, like water, then that might form an ocean or an atmosphere like it did on the Earth. So outside of the rock again. Now, some asteroids they're not that primitive type of object. They were actually part of a body that was on its way to becoming a planet. They were half built when they were smashed apart in a giant impact early in the solar system. So they might actually be the piece of a core of a planet. So when you're looking at those iron meteorites, that was a lot of the time from a planet that could have been in the solar system but wasn't, or the crust of one of those planets. So a lot of them are these fragments of smashed apart, half-built planets. Now, where are they today? So you might have heard about the asteroid belt, and it's between Mars and Jupiter. So you got Mars's orbit here and Jupiter a little bit further out. And the asteroid belt is this cluster of them around there, and it's kind of like a cosmic rubble pile. They're there because the other planets aren't. Everywhere else, the planets have kind of swept out their orbits and kind of either thrown things out or brought them in and incorporated them into building that planet. But there isn't a major planet here, so these things have been free to keep orbiting the sun. And if you were to look at that from above, and you could actually see them all, it looks like this giant swarm of them. And that makes it look like there's this huge, there are enormous amounts of them, especially in numbers. But if you were to actually go in there, you wouldn't really see much. It doesn't really look like this. These dots are way bigger than the asteroids themselves. So it does not look like when you're in Star Wars and you're racing between the asteroids to escape the Federation, the Empire, to escape the Empire. It's not quite like this. The asteroids are actually way further apart in the asteroid belt. The typical distance between asteroids in the main asteroid belt is twice as far as the Earth and Moon are from one another. So it's like 600,000 kilometers. It's an enormous distance between them on average. So you run very little risk of actually running into an asteroid. Now, how do they actually get here? How do they get to the Earth? So in this plot, what we're looking at is you've got the distance from the sun. We call that AU, and that just means Earth is 1 astronomical unit from the sun. Jupiter is out at 5. And then you go up here, you kind of, on that axis, you've got kind of the inclination. So how most of the planets are in a nice flat plane, but a lot of the asteroids are often inclined to that. So they're going like this, whereas the planets are going more like, I don't know if that's clear in the video, but like that, and they're going like that. And what you can see is, so in these clusters in that main belt, there's brighter patches, and those brighter patches are where there's a lot more asteroids. And you can also see gaps, these lines in the asteroid belt, and those lines are caused, these ones in particular are caused by Jupiter. And Saturn also has a big influence, but it just doesn't look like these lines. But that is where there are something called resonances, where Jupiter and Saturn, their gravity tugs and pulls on the asteroids in these regions, and it throws them out, it flings them out, or stretches their orbit into long ovals until they start intersecting with Earth and Mars in the interior. So it's Jupiter and Saturn's gravity that actually throws them out of the asteroid belt and into the inner solar system and into paths that intersect with the Earth. So that's how we get these near-Earth asteroids, ones that actually impact. So either coming past very close to us or impacting us, like it did when one wiped out the dinosaurs 65 million years ago. Now, if that's happening regularly, which it is, then it's a fair question to ask, well, what's the likelihood of that happening tomorrow? And there's a 100% chance, in fact, that we will be hit by meteors tomorrow. It's just that most of them are tiny things called micrometeorites. So we actually get tons and tons of this material raining down on the Earth every single day. Raining down, and some of it, pretty regularly as well. We get these more like fist-sized kind of clumps, meteorites raining down, and those big ones are much more rare. And we are actually trying to track the big ones that do have potential impact risks. So tomorrow, unlikely to have a big one. But within the next century or so, in the next 2 centuries, there is not a, it's still unlikely, but it's still not great odds when you look at the outcome of it. So Bennu here is 1 in 2000, has a 1 in 2,700 chance of hitting the Earth between 2,175 and 2,199, and that would be very bad. Bennu would destroy whatever region of a continent that it hit, and kick up a lot of dust. It would be a very bad thing to have happen. So part of the reason that NASA sent the OSIRIS-REx mission to Bennu was, one, to understand it, because it's one of these carbonaceous chondrites, those ones with a lot of water on them. So it's kind of interesting for that reason, but also because it's an impact risk. What can we do about it? Is there, like, studying its structure? If it's a rubble pile, we can't really push on it because it means that you'll just kind of break it apart and it'll have a lot of impactors. So what do you do about it? One idea is that we could use things like lasers, and you shine a bright laser at it and it evaporates either the ice or even the rock itself. And that then evaporates and acts like a thruster, like a rocket thruster on the asteroid, that deflects it away from the Earth. Yeah, that's quite an extreme example. There could be simpler ways, simply by painting it on one side. Now that would take a long time to take effect, but it would be much less dangerous than having a giant laser in space. And by painting it, you kind of change. It's in a similar way, but when you have if you imagine like hot tarmac like tarmac at the end of a summer day, it gets really hot. It's absorbed a lot of radiation. So if you were to paint one side white, one side black, for example, and then that dark side will be emitting radiation afterwards, and that glowing of radiation will slowly deflect its orbit and change its orbit in the same way that this thruster was. This thruster of like a plume of gas and dust caused by the laser, just over a much longer period of time. And impacts aren't necessarily all bad in a lot of ways. So life on Earth may actually owe a debt of gratitude to those carbonaceous chondrites, those wet mud bowl kind of asteroids, because they are also really rich in organic compounds. And organic compounds are the things that life is built out of. We find amino acids, which are the building blocks of proteins. And recently, actually, a protein was discovered in one of these. That doesn't mean that life is on these. It's just that the complex organic things that build life are inside them. So one idea is that these rained down on the Earth later in its formation, after it had cooled down. Once it wasn't a magma ocean anymore, you haven't got just lava everywhere. It's cooled down enough to have a liquid water ocean and solid rock, and then these organic chemicals rain down with these meteorites and slowly begin to complexify into what we call life today. So impacts may actually have a really important role in the creation of life on Earth. Now I've got a question slide here, but unfortunately this is a pre-recorded version. But if you check out the video, there were some questions asked at the end with Eloise. And we answered those. So yeah, thanks for checking. Thanks for tuning in. See you later.